let's continue part 4, lecture 17, D3, Noether theorem. Now I will apply to the spatial translation. You see, then I will talk this later on this lecture. Now, this delta L variation of the Lagrangian, this is Lagrangian density. This is just L is a function, you see. This is the argument of L, okay. This is in general when we have a 4-dimension, but T here is explicitly involved. So this is a general. So I can derive here just using the variation of L. You see each. Attention now, this here is a variable. You see, in the classical mechanics, this is analogous to the Q dot. You see, this is Q in this case, phi is Q, and this partial derivative here is Q dot. Plus this partial with respect to time, in this case, delta x0. Now, consider now the variation only of this term over here. You see, that's important just to emphasize this term over here. See, this is over here. So, this one, this is a partial, attention now, partial derivative with respect to J, variation phi. I just swap, you see, these two operators here, this, and just wrote that. So I'll call this equation 1, this equation 2. Substitute, in this case, the equation here, you see easily that I can obtain this, just substituting, you have this expansion here. Now, consider this term, you see this over here, you see? Now, you can use the product rule, okay? Integration by parts. I just call this U, this V prime. So this derivative, partial derivative, that UV minus U prime V. This is from calculus. You just look at this term, and then I repeat over here. So I can group, you see, this variation phi, okay, in just over here. You see, that's also, let's mark this one here. You see, this one over here, and this one over here. So you just group, and then just write this easily. And this is Euler Lagrangian. So this must be equal to 0. So this leads to only upon this term here plus this term over here. Now, since I want a spatial translation, you see, only the coordinates can vary. So this time here is constant. So there is no variation of time. Then I set this to equal 0. And now that's for you to pay attention, because phi of x is phi of xi. You just a way to represent. And don't forget, I here is 1, 2, and 3. Okay, that's the coordinates. Now, from here, I will show the very, very important, you see, relation, which is just over here. You see, a spatial translation, you have delta xi is just, I can write over here like this. So this is equal, this is x prime, okay, minus x. See? This is delta xi. This x prime is another coordinates. See? This will be x prime 1, comma, x prime 2, comma, x prime 3. So the difference over here, you see just that's a small increment, epsilon I. It's better to write, to be consistent. I put right here and I there. So now you have to pay attention on this relation. You see the variation of phi xi is equal to this difference of here. Attention on this. Xi is the same. You see, this is not like x prime I. You see, attention now. This here, okay, xi. Because why? I want to have the variation of phi at ci. You see, it's different. Attention now. Phi prime, c prime in this case, x prime I. It's not x prime I. You see, that's the same point over here. I will show here a numerical example why this minus sign here. So, this is a numerical example just to show, to demonstrate that this leads to the minus sign over here. So, let's consider the spatial translation. X prime I is equal xi plus epsilon I. Exactly, pardon here, there is a plus sign. This over here is, that's right, okay? This is equal, let's write this way. So I just copy from here, x prime I is equal xi plus a small increment, xi. Just a copy from here to here. So I want to emphasize that C, in this case, the phi, is a scalar quantity. Okay? So phi prime at this point is different from this case of phi at x. You see, because the scalar, like temperature, okay, temperature at one point is different from the temperature at another point. That's what is written over here. And the scalar function varies with respect to the space. See? This case, x prime and x. So let's compute, attention now, this difference here. You see the blue one, that's the same point x. I want to derive, just show you a numerical example, this difference here at the same point. You see, x1, x2, and x3. The same point. It's different from here. This is x prime. So, as an example, I will work only in one dimension. See, let's work with x1. Let, as an example, it is phi t x1 is equal to t squared plus 3x1. See, that's a function, a scalar function. And now, x prime 1 is this case, is x1 plus x1. I just working here, okay, or here, for I is equal 1. That's a particular case. And also, remember that J over here is a dummy index. But just here, in this case, I just set j is equal 1. Okay, only one term. So then here, now I have this point. See, for 3, 2. You see, 3 over here, the time, and 2 over there. This is 2 here. You see? See, that's a point I call point P. Okay? There's a point P. Point P. So you just substitute, see? T over here and x1 over there. So this is equal to 15. And assume that the small increment in green is 0.01. Now I can express x prime 1 as x1 plus 0.1, 0.01. Now, attention now, that's a point Q. You see, when I substitute, okay, the point, attention now, this is 2, this is 2.02. You see, I'm working this epsilon over here. So this point over here, Q, is just 3, the same. Attention now. And now I'm worried about, by hypothesis, the spatial translation. The variable t, okay, is constant, okay? I assume this the same value. You see, you can see on this example, you have 3 over here and 3 over there. But x1, this x1 plus